Okay, hi everybody. In this video what I'm going to do is derive Snell's law for you using Fermat's principle. And to remind you, Fermat's principle is if you have light traveling from one medium to the other, and this is the boundary between the two mediums, that the path the light will take will be the path that minimizes the time between 2 points. So, of course, we in physics are used to what's called Snell's law, and it tells us, we also call it the law of refraction, saying if you go on one side, light passes through the medium on one side with the index of refraction n1, and you make some angle with respect to the normal for that light beam, it comes out at a certain angle, theta 2, into the other medium, which has an index of refraction of n2. So we want to show how this comes about from Fermat's principle, using the calculus of variations. So we want to minimize time, and here's our light path. One medium to the other, here's n1, n2. So the light travels a certain speed v1 on this side, and speed v2 on this side. Let's look at a little ds. This is just like we did with the brachistochrone problem. We're going to say that length we can write as dx squared plus dy squared, take the square root, is ds. And we can also write that as, I'm going to divide both sides by dx here. We've done this. I'm going to rewrite that as ds equals dx squared divided by dx squared is 1 plus dy divided by dx squared is y prime squared square root, and I'll pull out then a dx. So just to remind you, I guess I skipped some steps here, but this is what I did. Divide both sides by dx squared, and the time, dt, is going to be that small distance traveled divided by whatever the velocity is at that point. And that velocity is different for both sides. Now, Euler's equation, what we're trying to minimize then, is, this is J, minimize the time. So we get the square root of So here's what we're going to do. We're going to assume when it's over on this side that the velocity is a constant v1, and when it's over here it's a constant velocity v2. So v down here does not depend on position, except for when you cross the boundary here. Okay, so this is what we're wanting to minimize. This is our time. And we realize that this is the functional. This is f. It depends on y prime. Okay. So Euler's equation is partial of f with respect to y minus d dx partial f with respect to y prime equals 0, where this is f here. So again, this is necessary to have a minimum time here. So this is 0 because f does not explicitly depend on y here. So what we have is this, that d dx, the partial of f with respect to y prime, is equal to 0, and that implies that the partial of f with respect to y prime is a constant. So what is the partial of f with respect to y prime? That's equal to, I pull out the 1 over v, 1/2 square root of 1 plus y prime squared times 2y prime. Y prime over v square root of 1 plus y prime squared. So that is equal to a constant. So that means that's the same on this side of the boundary as on this side of the boundary. So we have this quantity on one side of the boundary is equal to that quantity on the other side of the boundary. But this does not look like Snell's law. So to do that, let's look at ds here. ds, remember, is a little dx. I'm sorry, it's dy on that side, and it was dx this way. Now if I take all of these things and I divide by x, what do I get for dx? This is dx over dx, which is 1. This is dy over dx, which is y prime. And this side, of course, ds over dx, this is the same as writing 1 plus y prime squared, because it's a right triangle. So what we get from this is that, let's say this is theta with respect to this axis, and here's our boundary. So we get that y prime is tangent of theta, and we get 1 over the square root of 1 plus y prime squared is equal to the cosine of theta. So y prime over v square root 1 plus y prime squared is equal to tangent of theta, sine theta, over cosine theta. I have the v down here, right there. And then 1 over 1 plus y prime squared, the square root of that is cosine theta. So we get that's equal to sine theta over v. So what we get now is that this thing is a constant, but we can write it like this, so that we have sine theta 1 over v1 when you're on this side. It's got speed v1 is equal to theta 1 is equal to sine theta 2 over v2 on this side. Of course, that still does not look quite like Snell's law, because Snell's law uses the index of refraction. So the index of refraction is defined as the speed of light over the speed of light in a certain material. So speed of light, in a vacuum over the speed of light in the material. So that material then has this index of refraction. So we would have, for v1, we could write v1 down here as c over n1, index of refraction of this side, and we would have v2 equals c over n2. So if I go back up to this, I have sine theta 1 over v1, which is c times n1, equals sine theta 2 over c times n2. So that's Snell's law. There we go.